In part one of this video, we looked at the properties of this normal distribution, and we invoked something called the 68, 95, 99.7 rule. In that rule, what we saw was that a normal curve is distinctive because it can always be carved up into specific pieces of area. You may remember this picture. In this picture, we can see that for a normal curve, and again, this is only for the normal distribution, which does not describe every type of data that's out there, in between one standard deviation below and one standard deviation above the mean, there is 68% of all the data. Between -2 and +2 standard deviations, there's 95% of all the data. And in between 3 standard deviations above and below, there's 99.7% of all the data. We also looked at another graph that kind of split this picture up into vertical strips. Those vertical strips are sometimes helpful to know because then you can combine them together. But keep in mind, you can also take some of these numbers given in 68, 95, 99.7 and split them up to use them as well. But here's the key question today. Well, what if I'm working with numbers or I'm interested in knowing something about them and they don't fall on these nice standard deviation breakdowns? What do I do then? So let's go back to the problem that we were talking about before. In this problem, you had a distribution of men's heights. And you may remember this from before. It's probably still on your paper if you took notes on it. We said that men have heights that are normally distributed with a mean of 69, which put that right in the middle of the curve. Now you can tell drawing normal distributions is not nice and not easy to do, so don't beat yourself up if your distributions don't look great. Mine don't look great either. Also remember, though, that we had 3 standard deviations going above and below the mean. So one standard deviation above was 71.5 inches, then 74, then 76.5. Okay. We could also say then on the other side, we had 66.5 inches, 64, and 61.5. Now we could answer a whole bunch of questions like this. We could say, for example, that the shortest 50% of men are generally 69 inches to 61.5 inches. There are men shorter than that, but their numbers are really, really small. If I wanted to say what's a reasonable range of heights for most men, I would either say something like 66.5 to 71.5 inches. That would take care of almost 70% of men, or 64 inches to 74 would account for almost 95% of all men. A man who's outside that range would be considered unusually short or tall. So what we're going to talk about now is, let's pick a number that's not among these nice numbers and talk about what we would do with it. For example, let's say I wanted to find out something about a man who is 70 inches tall. That would put him somewhere kind of in this range right here. That's where 70 would fall. And so we're going to look at how would I analyze that man. Let's say, for example, I wanted to find his percentile ranking. How would I do that? The first thing I'd have to do is I'd have to know, just by looking at my graph, I know he's between 0 standard deviations, that would be the mean, and 1 standard deviation above the mean. But where exactly is he? So the first thing I'm going to do is take my formula for Z, and I'm going to evaluate it for a 70-inch tall man. So I'm just plugging in X minus my mean divided by my standard deviation. So then I'm going to take my calculator and go 1 divided by 2.5, which gets me 0.4. That seems reasonable since I knew his standard score would have to be between 0 and 1. He's above average, but not by a lot. Well, if I want to find his percentile ranking, what I really want to know is how much area is there to the left of his height. Now to do this, I know it's going to be a little more than 50%, but it's not going to be as much as, let's see, that would be 50. It won't be as much as 84%, because in order to be at 84th percentile, he'd have to be all the way up to 71.5. So I know it's not that high. But between 50 and 84, there's a lot of room for error. So the question is, where is he? In order to answer this question, I'm actually going to need one other tool, which is a table. In your book, it's inside the front cover. And what you're going to want to do is find it. It's called the Standard Normal Table, and I'll load it here for us Okay, so this is the standard normal table. I'm looking at the page and notice that it has two sides to it. On one side you have z-scores listed in the left-hand column right here. And on one side they're all negative, and on one side they're all positive. Right now the score that we were talking about is a positive one, so I'm on the page with the positive scores. You may remember that the score that we just calculated is 0.4. So what I'm going to do is locate that row on my table, and it's right here. Okay? And you may wonder, what are all these numbers going across? Well, in our case, Z was 0.4. Now that's really 0.40. We didn't write another 0 behind the 4, but we certainly could. The numbers across the top of the table allow you to look up values for numbers like z equals 0.46. In that case, I'd be on the same row, but I'd be looking at the element here underneath 0.06. So these two parts together make the value for z equals 0.46. That's not the one that we're after, however. What we're looking for is for 0.4, which is right here. It's the very first number in that table, 0.6654. So going back to our picture that we had, remember we had this picture, and I'm not going to draw the whole thing again with all the numbers. I'm just going to remember that if 69 is in the middle, 70 was a little bit to the right of that, and we really wanted the area to the left of that. We already calculated for that value that z is 0.4. From what we just saw, the area that goes along with that is 0.6657, which is right in the range we thought it would be, between 50% and 84%. So it would basically be at the 66th percentile. Now, one other thing you may notice about this table is that there's actually a picture that went along with it. We'll take a look at that. So if you go back to your table, I want you to notice this picture at the top of both of the pages, because what it's showing you is it's saying if you look up a particular z, which is shown here in the bottom of the table, or I'm sorry, in the bottom of the picture, it's showing you this shaded section right here. It's saying that's the area the table will give you. Not every standard normal table is set up the same way, but most of them are set up in this way. That means if for some reason I didn't want to find this area to the left, let's say I wanted this area to the right, I might have to do something with the number in my table, like subtract it from 1 to find the area I'm interested in. Let's try a question kind of like that. So let's say, for example, that I had, back to my distribution of men's heights, it's a normal distribution with a mean of 69 and a standard deviation of 2.5. Let's say that I want to say what percent of men are between 65 inches and 70 inches. That's a typical type of question we'd want to answer. And if you say, who would want to know that? Well, if I'm Levi Strauss, or I manufacture clothes for Walmart, or whoever, I would want to know the answer to this question because I might want to make enough clothes of a particular size, more of some sizes than of others, and part of a person's size is dependent on their height. So how are we going to approach this question? Well, one of the first things we're always going to do with every single one of these questions is we're going to make a picture. If you do a standard normal problem and you do not draw a picture, you will not score proficient, period. So get in the habit of drawing a picture. So let's make a sketch. Remember that we're going between 65 inches to 70 inches, and that's the part of the graph we're interested in. We still have the same distribution as before. So we're going to make a quick sketch. This is not going to be something we're going to try to draw perfectly every time. All right. In the middle, 69. 70 is just slightly to the right of that. Remember, we could go 3 hash marks above, go 3 hash marks below. And in this case, what I'm going to do is just think about where would 65 be approximately. Well, I know the first increment down was 66.5. The next one down is 64. So 65 would be just a little ways above that. So there's 65. So I'm looking for the area in between those two values. It's kind of an irregular shape. The table that we just looked at only gives me area to the left of a particular value. So let's see what we can do with this particular problem. First of all, we need to know how these two heights are as standard or z-scores. And the reason I stuck with 70 inches is because we already know the z-score for that. We have already calculated it in the previous question. It was 0.4. So we're not going to calculate that again. Now we're going to have to calculate another one. To keep the z's straight, I'm just going to go ahead and call this one z1, just to keep it straight from the other z, which I'll call z2. That one's going to be found by taking 65 minus 69 divided by 2.5. And that's going to be negative 4 divided by 2.5, which is negative 1.6. Why is it negative? Well, remember, in this case, that's because 65 inches is below the average. In this case, about 1.5 standard deviations below. So we're finding the area for this other question, or for this other picture. You could think of it this way. I'm really trying to find the area between negative 1.6 and 0.4 if I'm looking at this as a standard normal question. Okay, this is the same area. What I'm going to do now is think about what I've learned from my table. Well, last time we looked up a value in the table, you might remember that we did it by first of all finding the page that had the positive z-scores on it. And so for z1, the area that we found in the previous question was 0.6554. That would be the area if we went from 0.4 all the way to the left and did not stop at negative 1.6. The problem is if I look up z2, I'm not going to get the area that I necessarily have shaded in my picture. First of all, I'm going to have to use the other side of table A, the part that has the negative numbers on it. I'm going to look at negative 1.6. You can stop the video for a second, try looking that number up, and then check it with the video when you're done. The number you should have gotten from the table is 0.0548, but on my picture, where is that? Well, it happens to be this area in this little tail right here. This would be 0.0548, but that's not what I want. What I want is only the black part that I have shaded. To get the shaded area, what I just need to do here is subtract 0.6554 minus 0.0548. That's going to give me what I'm really interested in finding. And in this case, that's going to be 0.6006. Or in other words, if I wonder what percent of men are between 65 inches tall and 70 inches tall, it's approximately 60%. The last type of question that you're going to be called upon to answer in this type of problem would be one where, say for example, we're trying to figure out something based on knowing what the area is first, but not knowing the height that it goes with. So for example, we could say, what height is at the 90th percentile? Still talking about men's heights, still talking about them being normally distributed with a mean of 69 and a standard deviation of 2.5. Well, that's kind of weird. Normally what we would do first is try to calculate a standard score z, but we don't have enough information to do that because we don't know what height we have. That's what we're looking for. And in this formula, I would type in or I would plug in my mean, my standard deviation, and x, but I don't know x. I also don't know z. The only thing I know is that I'm at the 90th percentile. I can draw a picture of that. So here's my picture. The 90th percentile would mean that I have 90% of the area to the left of that value. That's a lot of area. That's most of the curve. So I'm going to put a line over here somewhere. I don't exactly know where it should go, so I'll make it my best guess. And I know that this area in here is equal to 0.9. And I'm just going to put z down here because that's kind of what I have right now. And that's all I know. In this case, what I really need to know is I need to know what z would give me that area. If I could find that, I'd be in good shape. Let's go back to the table one more time. Okay, I'm back on the table, only this time I don't know what z to look up, so I'm going to look at the numbers in the body of the table. I'm looking for numbers that are really close to 0.9. I can find two of them right here. Notice that 0.9 isn't in the table, but there are two values that are very close. We have 0.9015, which is off by 10 thousandths, and then we have this number, 0.8997, which is just a hair closer to 0.9. So it's probably the best option that we have. It's in the row for 1.2 and the column for 0.08. So the z we are going to use here is 1.28. Now that we have this number, we're going to go back and see if we can finish our problem. If z is 1.28, remember that's also the same thing as x, which we don't know the height, minus 69 divided by 2.5. And the question is, could we possibly solve that and find out what x is? And of course the answer is we sure can. So we're going to take 1.28 times 2.5, because all we're essentially doing is multiplying both sides of the equation by 2.5 to clear it from the bottom of the fraction so it cancels out. And we're going to have that product equal to x minus 69. So 1.28 times 2.5 is 3.2 equals x minus 69. And you can almost think of this 3.2 as being the number of inches that represent 1.28 standard deviations. That's converting it back to inches. Now if I add 69 to both sides, I'm saying how much height do I need to add? Oh, that was backwards. How much height do I need to add to 69 inches in order to get to 1.28 standard deviations? And of course we know that's going to be 72.2 inches. This is sometimes called a backwards calculation because instead of starting with a z and working to an area, you're starting with an area and working back to a z. You should try an exercise on your own or two and see if you can get some correct answers to an odd numbered exercise.